Stepper motor driver upgrades part 3 for the TMC2130 including sensorless homing. As the title suggests, this is a third in a series on upgrading your stepper motor drivers. Previously we looked at the basics including the A4988, DVR8825 and the TMC2100. And then in the last video, we looked at the TMC2230, including UART mode. Today, we're looking at the Trinamic 2130, and it's another step up in terms of complexity compared to the 2208. But before we start, let's go over some reminders. You can't perform this upgrade if you're running a mainboard with integrated stepper motor drivers like the Ender 3. Instead, you need a ramps or ramps compatible board where there's a slot to plug in a separate stepper motor driver and you can change them at will. This guide is based on the MKS Gen L, and I previously made a guide on how to fit this to an Ender 3. Just like the others in this series, the Trinamic chip is the actual driver in the middle, and the rest is the breakout board from various manufacturers. There is variation amongst these, as you'll see in this video, because I'm testing with two different Chinese brands. As you'll see, one of them is a lot easier to use than the other. There's even variation between the different versions from the same manufacturer, so read the sheets carefully before you purchase. Hopefully you now know whether your 3D printer is ready to accept one of these upgrades, so let's have a closer look at the 2130. The TMC2130 is yet another offering from Trinamic. Much of its specs are very similar to the 2208. It can do 1/16 microstepping with interpolation up to 256 steps, and it can also be configured through SPI for 1/256 native microstepping. Compared to budget offerings, it is quiet, and it has stealthchop mode as well as spread cycle if you need more torque. It can run in standalone or use SPI communication to talk to the firmware. The downsides are it's more expensive, it may skip steps in stealthchop, it runs hot, and it is time consuming to wire up. Compared to the 2208, the main point of difference is the fact that it has stall detection and stall guard too. This means the driver can detect missteps or collisions, and that means we can enable sensorless homing like you see on the Prusa MK3, which has 2130s from factory. Just like with the TMC2208s, we have more than one operating mode, and we're going to look at two in this video. The first is standalone mode, and it's meant to be a drop-in replacement for A4988s, and the second is SPI mode, which has dynamic communication between the mainboard and the stepper motor drivers where advanced settings can be set. We're going to start with standalone mode, and we're going to look at how to configure the jumpers on the mainboard, set the VREF, and make any necessary changes in the firmware. One of the boards I was working with came default in SPI mode, so I needed to do some configuration. Fortunately, that was as simple as bridging two solder pads to put it into standalone mode. The other brand from Big Tree Tech, I had inadvertently bought standalone mode already, so they were ready to go for this part of the testing. If we look at the pinouts for these boards, we'll see that where on an A4988 we would have had configuration to set our microstepping, the same pins here are for the SPI communication. Therefore, on your mainboard you should remove all three jumpers before installing these. With the SPI pins likely facing up, it probably won't make too much difference, but there are some versions that have the pins facing up and down at the same time, so better to be safe than sorry. So as you can see here, these boards have variation in which the one on the left has the chip on the top and the one on the right has a chip on the bottom where it typically is. Therefore, you should only rely when you're plugging it in on looking up the ground and direction pins and matching that to what's labeled on the main board. We're plugging in both of these now with the aim of setting the motor current by way of the VREF. First things first, always connect the 12 or 24 volt power supply instead of the 5 volts from the USB. Set your multimeter to a max of 2 volts DC. The black or negative probe from the multimeter goes to the negative input from the power supply. And the red probe can go in two places. It can either go directly into the trim pot, and this is the same on both models, or you can put it in the via that's part of the triangle closest to the enable pin. What you're seeing on the multimeter is the current voltage reference or VREF. There's a really efficient way to adjust the VREF, and that's to take an alligator clip, put one end on the probe, the other on a small flathead metal screwdriver, and then as you adjust it, you'll get the reading in real time. As you can see, very small adjustments make a big difference. Also note that this Big Tree driver works in reverse, which means turning it clockwise lowers the VREF. As for calculating the VREF, in part 1 we did the research for the Ender 3 and found that it takes 0.84 on X, Y and Z and 1 amp on E as the maximum. Kevin Quinn rightly pointed out that this information is available on the Ender 3 GitHub, so I should have gone here first and saved myself some time. TMC drivers are unusual in which they need RMS current, which is more of a typical or average current, rather than the max current to calculate the VREF. Fortunately, to get this, all we need to do is divide by 1.41, so on Ender 3 that gives us 0.596 for X, Y and Z and 0.709 RMS for the extruder. Now we can put these values into the VREF formula, which is RMS current times 2.5 divided by 1.77. For the Ender 3, crunching these numbers gives us 0.842 volts and 1 volt on the extruder. However, we don't want to run the motor at its max, so it's safer to reduce this to 90%, which gives us 0.76 volts and 0.9 volts. One thing I've been doing in this series that might be a nice tip is to mark the higher VREF extruder stepper motor driver with a Sharpie, so that way I don't misplace it and put it in the wrong axis later on. Next up, we're going to install the heat sinks, and on the Big Tree Tech it simply goes on top of the driver. On the other one, the driver's on the underside, so we line it up with the thermal pads on the top and we insert it firmly into place. Now it's time to set up the Marlin firmware. If changing from A4988s, there's only one thing that needs adjusting in the firmware. In configuration H, search for invert_X, and then toggle between true and false for any axis that you're installing one of these stepper motor drivers. Now before we switch to configuration ADV, we're going to search for one more thing, and that's 2130. That'll take us down to the stepper motor driver section, and I had some questions in the previous video on the 22.8 where I didn't put in TMC2130 standalone. If we paste it in, tick search all sketch tabs and continue to press find, we'll find very few references to it elsewhere in the firmware. The same goes for 2130 standalone mode, and in conditionals post are the only references we'll find to it. As you can see, there's subtle things to do with stepper motor rates and timing of pulses and stuff like that. I would say that it's more correct to set it to standalone for either of these drivers, but the 2208 and the 2130 are designed to be a drop-in replacement without any of this configuration, so you should be good to go either way. Time to save and upload the firmware to the board. Like the 2100s and the 2208s, by default these drivers will be operating in stealthchop, which offers really smooth and quiet operation. I like to test the sound by doing a homing test because it's consistent, repeatable, and there's nothing like the part cooling fan to interfere. I'd have to say the noise level on these is identical to the two other TMC drivers that I've already tested. It's so much quieter than what you can expect from your standard stepper motor drivers that you get on most budget 3D printers. I got going on my test prints with this high-speed one designed to provoke layer shifts, and this benchy to test the quality. Once again, I decided to test the temperatures of the stepper motors as we went, and there was no problems. Remember that the critical point is when the stepper motors get too hot to touch, and this is nowhere near that, so I think our VREFs are spot on. Anyway, let's have a look at the results of the test prints. Our 100 mm per second speed test once again has no skip steps or missed extrusions. So now onto the benchy, and once again a reminder that you should ignore the Z banding at the bottom. That's damage to the lead screw and nut. Beyond that, there's no blemishes at all, no surface artifacts, and no missteps or layer shifts. Again, no signs of skipping or any print artifacts. This stealth chop mode, at least on small printers like the Ender 3, seems to be more than capable enough. Anyway, let's go on to SPI mode, which is really the reason you would fit these stepper motor drivers in the first place over one of the cheaper models. Like the 2208s with their UART connection, Marlin will communicate this time with SPI to the stepper motor drivers, and we'll be able to set a lot more parameters. We need to start by configuring each driver ready for SPI mode. Now the brand I don't know how to pronounce has the simple pads that you just need to desolder to put back into SPI mode. Couple of seconds and it's done. Doesn't get much easier than that. The Big Tree Tech needed 3 changes and they were minuscule little pieces. Here it is done. You can just see the bridges I made on the left and on the right you can see where I had to remove that little resistor to put it in SPI mode. For this hassle, plus the fact that the general quality control wasn't very good with bent pins and a heatsink that fell off every time I looked at it, I wouldn't recommend buying this version of the 2130. Now we are ready to do some wiring, and compared to the 2208, it's a lot more involved this time. Anyway, I'll take you through step by step. Inside Marlin, when you expect the MKS Gen L pins file, there's an awesome Easter egg. A link to this. Jackpot and thank you, Gerson Ramos. I'll be following this from this point onward. It seems like there's a lot going on here, and that's because there is. It's also partially because some of these wires are shared. We can see for STO, SCK and SDI that they daisy chain between the 4 axes and then plug into the mainboard. I'm going to make up these ones first. The DuPont crimping set and crimper are linked in the description below. It's a pretty handy thing to have if you're ever tinkering on 3D printers. We start by cutting and stripping 4 lengths of wire, 3 short and 1 a little bit longer. After that, we twist the ends together in a chain, as can be seen here. Anywhere where you have exposed wire, you're going to crimp on a female DuPont connector. Where 2 wires are twisted into one, it can be a little bit tricky, but take your time and everything will go together nicely. Here it is with all of the female pieces crimped on. If we refer back to our diagram, we can see that it plugs into the left-hand pin on each stepper motor driver. We take a 4-pin plastic housing, we find the left-hand pin, and then we slide it into place until it clicks. The double ones once again are a little bit trickier, but if you press them firmly and press them straight, they will eventually click into place and be secure as well. We can see that where this plugs into the mainboard, it's in the top left of the 3 wires. Therefore we'll get a 2x2 housing, locate the top left, and slide it in once again until we get that satisfying click. We can see from the wiring diagram that we still have 2 more of these daisy chain sets to make. Here they are crimped and ready to insert, and here they are inserted into place in the 2nd and 4th positions. The mainboard end has also been completed to match the wiring diagram. For the 3rd pin on each stepper motor driver, we have the CS pin which plugs in individually to the mainboard. I'm going to use a 3x2 6-pin connector. Here are the 4 CS pins plugged into the 3rd pin for each stepper motor connector, and here is me plugging them into the 3x2 connector, matching up the wiring diagram to ensure they're in the correct place. When the last one goes in with that click, that's it, our wiring loom is complete. Plugging in the loom to the 4 stepper motor driver connectors is really straightforward. What we need to take more care with is plugging in the other 2 parts of the loom to auxiliary 2 and auxiliary 3. The 2x2 goes into auxiliary 3, and it's a 4x2 set of pins, and we plug it into the middle 4. The CS pins go into auxiliary 2, and again we leave 2 pins spare either side and make sure that it's centered in that plug. My last tip is to get a white texture and label each one X, Y, Z and E, and then label number 2 and number 3 for the 2 auxiliary plugs. If you're ever pulling this apart in future, this will make it easy to get everything back into the right place. That wiring diagram is linked in the description below, and for me it was definitely a relief to get that done. It took me a couple of hours and I made up 2 at a time, and if you really want to avoid this, it's possible to buy the looms pre-made. Let's move on by configuring the firmware. On the Marlin firmware page, if we come to documentation, hardware and then Trinamic drivers, we'll receive this page here, and it has a summary of what is supported by the Marlin firmware. If we scroll down to features and configuration options, we'll get a summary of all the things that are to come in the firmware. So if there's something in this video that you don't understand, please follow the link and read up on it further. We're back in Marlin in configuration.h, and we're going to search for 2130. And that will take us down to the section where we declare which axis we've installed it for. We come up and we copy TMC2130 and then we paste it for each one. It goes X, Y, Z, and then you have to scroll down to E0, which is the first extruder. Don't forget to uncomment these. We're now going to turn our attention to configuration advanced and once again search for 2130. That brings us to the TMC Smart section, and this is going to be very similar to what we did for the 2208s. You'll note here it's telling us we need to install a library, so to do that we'll come to Sketch, Include Library, Manage Libraries. We're once again going to search for 2130. There will be at least 2 options that come up, and we're looking for, in this case, the second one, and I'm not going to try and pronounce that name because I know I won't be able to do it. As far as I can tell, this is a generic library if you're tinkering with another project, whereas this one here is written specifically for using with Marlin. You can see I've already installed, but if you need to, click the install button. Okay, we come down to the section where we can set our current for each one, and with the calculations, the RMS current ends up being the exact same number as the VREF. So we can enter this here, and for the Ender 3, that was 760. Once again, scrolling down to find E0, and the value for that was 900. Like the 2208s, you can set native microstepping all the way up to 256. I'm going to leave mine at 16. There was a comment on the 2208 video doubting whether an 8-bit processor could keep up with 256 microsteps, so I'm going to leave mine on 16, and I'm going to leave interpolate to true. Now we can see we've reached a section on TMC2130, but this is only if you want to override what's already set up, which we don't want to do with how we've wired everything, so we can keep scrolling past that. Here we can turn stealthchop off by adding a comment at the start to undefine it, but I'm going to take that away and leave mine enabled because I think it's a great feature. Make sure you uncomment monitor driver status. That'll give us access to these G-codes just above to find out some diagnostics. And then we have hybrid threshold, which is one of the main advantages of connecting the 2130s in this way. It allows us to have the best of both worlds for being quiet but talky when required. I'm definitely going to enable that. Now the 2130s have store guard too, and that's something we can use to enable sensorless homing, but we're going to leave that for a separate section of the video. The last thing that you should do is uncomment define TMC debug, and that will give us additional info when we enter M122 via G-code to find out how our drivers are doing. After this, we can save, compile, and upload to the board. Like the 2208s, we want to confirm that the communication is working well in our SPI mode. Therefore, we're going to connect via console. So here we are in Pronterface again. You can also use Simplify 3D or the terminal in Octoprint. And we're going to go to connect, and like with the 2208s, we're going to type in M122. We can see that we have a bunch of information here, and the driver registers all have an address here. If they all had zeros or Fs, it doesn't exclusively mean this, but there's a good chance that you have some sort of communication problem. In fact, with the 2208s, if something was loose, it would just degrade to legacy mode, but with these, it gives you a printer error and halts the whole printer if something isn't connected correctly. Now in this series of videos, you've heard the sound of the homing in a variety of configurations, but we haven't yet done it with hybrid threshold mode. Let's hear how that sounds. Personally, I found it interesting hearing the stepper driver switch between stealthchop and spread cycle during the same process. Before we do our test prints, it's time to have a look at sensorless homing. First things first, we have one tiny bit of soldering to do. For the X and Y drivers, you're going to locate the diagnostic pin, which is the one in the center on the end, and insert a single header and solder it into place. We don't need it for Z because we don't want the nozzle to collide with the bed, and the extruder never has to home. Back to our wiring diagram, let's show the only two wires left remaining for sensorless homing. These can be straight female to female jumper wires, and they plug in as follows. One side goes onto the newly created diagnostic pin. After this, you'll unplug your end stop and insert it into the lower of the 3 pins. Repeat this for Y and we're almost done. Almost done because I noticed it wasn't the best connection as it wasn't designed to take a DuPont connector. Therefore, on the real machine, I decided to put a couple of dabs of hot glue to prevent either of these from coming loose from vibrations from the printer. Ideally, you would find the correctly sized JST connector and crimp a DuPont connector for the diagnostic pin for the other side where it plugs into the stepper motor driver. We're back in Marlin to enable sensorless homing, and there's a few notes here above that we need to pay attention to. First of all, we need to set our home bump to 0. You can see as I search for home_bump, that's also in configuration advanced. And we're going to change that to 0 for X and Y. The next note we need to pay attention to is this M914, and we can use this to live tune the calibration. And the way that this works is that a higher number makes the system less sensitive, That means there's a chance that if you have it too high, it will crash without recognizing it as a home and just grind. And if the value is too low, it might be too sensitive, which means it might think it's at home when it hasn't actually collided yet. This is the first time I've set it up, so I'm going to leave it on the default values of 8 for now. We're going to start by uncommenting define sensorless homing, and remember we don't want Z, so I'm going to comment that out. One more little thing before we upload, we need to switch back to configuration.h and configure the end stops ready to have the single wire going in. So we're going to search for x_min end, and we need to set it to true for the X and Y. Now we should be able to compile and upload. Here comes my first test home. And as you can see, it's way too sensitive. Now, interestingly enough, when I connect via Pronterface, it says that my values are set to X0, Y0. So I'm going to try and set those now. M914, X, X8, Y8, which is what I thought I had set in the firmware. So that's a little too sensitive. I had one false positive, so I'm going to up these values to 10 and see how that goes. Now that I seem to have a value that's working for now, at least I'm going to do an M500 to save to EEPROM. Now I've left the factory limit switches in place because I figure it's nicer when homing to cushion up against those instead of smashing into the frame. It also means I can plug them back in if I have any problems in future. Now the value I ended up with tuning that was 12 after one more false positive, and I expect that I might need to tune that a little bit further in future. Something to look out for is that although I set this value as well as the hybrid threshold speeds in the firmware, they didn't really stay put until I set them via G-code and then saved them to the EEPROM with an M500. I repeated the same test prints again, and again I measured the temperature mid-print. Again, we had no over temperature concerns, and again when we inspect the print quality, it looks exactly the same. I'd show you this footage for longer, but you're probably sick of seeing it like now, and it highlights that the performance of these various TMC stepper motor drivers is pretty much the same unless you've got a bigger printer that requires higher current or something specific like that. So why would you choose this 2130 over the 2208? Well, the main advantage that it offers is the sensorless homing, and on certain printers that might be really desirable. I'll be fitting 2130s to my Frankendoodle Zortrax because the homing is inconsistent on the X and Y axis. 2130s are rated for a slightly higher peak current compared to the 2208s, but the same continuous RMS current. One other feature they have is cool step technology, but as far as I can see, there's nothing to support that in the Marlin firmware yet. Linked in the description is this table with a more detailed comparison of the 3 models that I've tested in the last 3 videos. And that should keep you going until I do a follow-up video with a more detailed comparison following some more extensive test printing. That's going to wrap up this video and this series for now. Please leave your thoughts and comments below. Thank you so much for watching, and until next time, happy 3D printing. G'day, it's Michael again. If you liked the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.